Take it away, Stephen.
Okay, so we're gonna hold questions to the end. And I mean, I've got lots of images to go through and try to tell it as a story, and we'll have time for questions at the end. And thank you, everybody, for coming. Thank you for inviting me. I greatly appreciate it. So I will share my screen and we'll get started. Let's make sure we are we seeing that first screen, everybody?
Yep.
Oh, phew. Boy, if she said no, I would have had to. Anyway, building Palomar Observatory, 1928, 1949. I guess I'd like to start with a basic point. See, this old telescope, your 200-inch telescope, has been in service now from 1949 to the present. It was the largest effective telescope in the world until the first of the Keck telescopes came online in 1993. And we are still doing great science. This old telescope is still supporting research in the disciplines of astronomy and astrophysics, very much at the leading edge of knowledge in those areas. That's a long time for a science instrument to be that productive. There are a couple of reasons it's that productive. It has remained in demand because it was so well built, because it's been so well maintained, the optics are excellent, and we upgrade the detectors virtually continuously. Well, of those reasons, I said it was so well built, that's what we're going to talk about today. And we're going to talk about how the optical system was created. So, again, well, hang on. I'm having difficulty advancing this thing. I don't know why. I may have to go out and come back in. We didn't have this problem the other day. Okay, let me work through that one more time.
Well, Steve, if all else fails, we could resort to that 3-slide screen we saw the other night. And it might be a little smaller, but you can still talk to it.
And we may need to. We may need to. Let me make one more try here. This is a problem I haven't run into before. And bingo. Okay, all set.
Yay.
So again, thank you for asking me to speak. I appreciate it. And let's start on what I think is a great story. of how Palomar Observatory came to be. The observatory is owned and operated by the California Institute of Technology and is funded by Caltech and its partner institutions. The 200-inch Hale telescope began science operations in 1949. We now support professional research on average 300 nights a year. The observatory was built with a $6 million grant, a whole $6 million from the Rockefeller Foundation that George Ellery Hale obtained in 1928. George Ellery Hale died in 1938 when the telescope was dedicated. In 1948, it was dedicated in his honor. Born in 1868, George Ellery Hale was instrumental in creating the science of astrophysics. He was a solar astronomer using a spectroheliograph of his own design. He demonstrated that sunspots originate on the surface of the sun in areas of strong magnetic concentration. Hale was a founder of Caltech, and he built the largest telescope in the world 4 times. Here we see his first 3. The 40-inch Yerkes refractor, 1897. The 60-inch Mount Wilson reflector in 1908. And the 100-inch Hooker reflector, 1917. Probably the most productive scientific instrument of the first half of the 20th century. Well, George Ellery Hale did those 3, but he always wanted more light. Always wanted bigger telescopes. He wanted to see further into the universe. And in April 1928, he published an article in Harper's Magazine called "The Possibilities of Large Telescopes." It was his way of conducting a public campaign to get funds and support for the building of a 200-inch telescope. And in that article, he set out 3 objectives. The 200-inch telescope would be used to study the structure of the universe, the evolution of stars and galaxies, and the constitution of matter. In addition to those 3 observing objectives, he also said that the new telescope would be used to support the development of new methods of investigation and new research instruments. Well, those 4 objectives, it is very much true that the science program here at Palomar Observatory still very much abides by those 4 objectives. That's very much the program that we still work on. Well, that was in April 1928, and George Ellery Hale, well, seems to have been fairly effective, and also, from what I understand, very persuasive. Excuse me, very persuasive. For in October 1928, the International Education Board of the Rockefeller Foundation awarded Caltech the $6 million to build the 200-inch telescope. And from that moment, they began design work. They did designs of the telescope, of the dome. They did a lot of things on paper because doing it on paper was relatively inexpensive. So they came up with all kinds of design proposals. This one by Russell Porter for the 200-inch in 1934, well, he was working towards a design consensus, but in the end, the 200-inch telescope looked nothing like this. Yet, 2 years later, he did another sketch, and this one very much reflects what the build was when they got around to actually making. This is pretty much what the telescope looks like. And see, this reflects a problem with the project. They were very careful about doing expensive things like building domes and building equatorial mounts and things like that, because they didn't know if they could actually make a 200-inch mirror blank, a 200-inch disc. And until they knew that, they did lots of design work, but other than work on the mirror, they didn't do any construction. Well, they did do work on the mirror. They had to get past that. George Ellery Hale knew that the mirror was going to be the pacing item of the whole project. After failure at General Electric, the contract was turned over to Corning Corporation, and Caltech asked Corning to make a 200-inch disc made of borosilicate glass, what we used to call Pyrex. They chose Pyrex because it has a low thermal expansion coefficient. And in this picture, these two pictures, notice on the right, what you're seeing is a recent picture of the mirror without its protective coating of aluminum. And you'll notice that there's a pattern. There's a pattern in the back. There's a pattern of voids, a honeycomb pattern, perhaps. And that's very important. You see, they put those voids in the back of the mirror to reduce the weight and to help it achieve thermal equilibrium more quickly, airflow behind the mirror. And they made those voids by putting cores, ceramic cores, on the floor of the mold. That's what you see on the left. All these cores sit there so that when the molten glass is poured into the mold, it has to go around the cores, and the cores can later be removed, leaving the voids. And you'll see, particularly, there's a big core right in the center. That's a 41-inch diameter core that was there to create the cassia grain opening in the center of the mirror. Well, with that, here we see them building the mold in the factory at Corning. And this is an image of the workers attaching the cores to the bottom of the mold. Note the steel bolts that are used to hold them in place. Well, with that construction done, they did a first pouring on March 25th, 1934. It was a big deal. Corning made a big deal out of it. It was something of a cultural event. It had a lot to do with the assertion of American competence during the Depression. And Corning invited the public into the factory to watch the process of pouring mirror. The process, the activity was broadcast nationwide on NBC radio network by Lowell Thomas. And here's a look at what they did. They had ladles take molten glass out of the melting oven and pour it into the kiln, 750 pounds per label. And they had to pour in 20 tons of glass to fill the mold. Well, that goes on for much of the morning, and the chief engineer and Corning's project manager, George Macaulay, kept a close eye on what was going on. And things went well until a little bit after noon, when all of a sudden they noticed that the surface of the mirror, the surface in the oven there, was disturbed. And what had happened was that the hot molten glass went into the mold and it melted those steel bolts. And the cores that were dependent upon those bolts floated to the surface and ruined the mirror. And that's what the ruined mirror looks like. A little hard to see, but there's something really wrong with the surface of that glass. Well, of course, Corning was very embarrassed by this very public failure. But the important point, by late spring 1934, Corning and the people at Caltech had figured what went wrong with this pouring. And they figured out how to fix it. They could fix it by making the steel bolts hollow and then blowing air through the back of the mirror, blank, excuse me. This was important. They figured out how to correct it, and this failed pouring showed them that they were able to make a 200-inch disc, 24 inches, actually 26 inches thick, 20 tons of Pyrex. And that understanding facilitated everything else that went on in the project. Particularly from there, excuse me, they committed to purchase of land on Palomar Mountain, and we'll get to that part in a little bit. But as I say, Corning was very, very embarrassed by this very public, everybody knew what happened. And they were, I mean, what do you do with 20 tons of useless glass? Well, they were so embarrassed that they put the failed mirror blank in their museum, where they now charge people money to see it. So from there, they went to a second pouring, December 2nd, 1934. It was an early Sunday morning. They did it in secret. Nobody was around. Just the people who would be pouring the molten glass into the mold and George Macaulay. Well, Macaulay, of course, keeps careful watch on what's going on. And after many months of cooling in the annealing oven, a 200-inch disc was produced that Hale and others at Caltech judged to be satisfactory. Not perfect, there were issues with it, but it was good enough. And the whole project fell out and proceeded from there. And here we get a good look at the honeycomb pattern in the back of the mirror. We get a look at a good sense of the size, how big this thing is. And that's George Macaulay on the left. And I'm not sure who that is on the right. I have not been able to find out. But with the mirror out of the annealing oven, they were ready to ship to California. And here they've put the mirror blank on a trailer, and they're going to drive it down to the railroad station at Corning, where they put it on a specially made rail car for the trip to Pasadena. The people at Corning encased the mirror in a protective metal shroud, and the train set off for the West Coast. And here you see the map from Corning all the way across to Pasadena. And they did 16 days to get across country at 25 miles an hour, stopping every night. Note in this map, there's a little jog, or maybe a big jog, right in the middle of the country. Well, the problem is the mirror standing on its edge like that stood so high that the train couldn't go just anywhere. In fact, there were some pretty tight squeezes as they moved across the country. And here the train is coming into the yards at Pasadena. Again, this was a big deal. This was a big deal. It was an important cultural moment. And schools all along the right-of-way let students out of class so they could see the train pass by. And here's the train arriving at its destination. Notice there are a lot of kids in the crowd there. Well, they took the mirror blank in its protective case, took it off of the rail car, put it on a trailer, and brought it into the optical lab at Caltech, April 10th, 1936. And here are the folks who are going to grind and polish that perfect paraboloidal curve into the upper surface of the mirror. So while that's going on, high atop Palomar Mountain, they had been doing seeing studies for a number of years. They'd been using 4-inch refracting telescopes like this, set to be able to look at Polaris as a constant, one constant source of information about turbulence in the atmosphere. And starting in 1932, a man named William Beach and his wife used a telescope like this one to take measurements of seeing quality on the mountain. Well, William Beach was a rancher in the area, and it happened that William Beach owned a lot of land up here. In fact, he owned a good portion of a plateau that is just below the true summit of the mountain. And that's the site Caltech, Caltech wanted to use for the observatory. So on September 21st, 22nd, 1934, people from Caltech, people from the Cleveland National Forest, people from the County of San Diego met with Beach and several other ranchers. And at that point, Caltech purchased from Beach 120 acres for the observatory. It was the point at which Caltech made a commitment, stuck a stake in the ground, so to speak, made a commitment to having Palomar Observatory be the place, or having Palomar Mountain be the place where the observatory would be built. We started 120 acres. By 1940, that had expanded to 1,400 acres, and presently we have about 2,000 acres on the mountain. Well, there were people from the County of San Diego at that meeting up here on September 21st, 22nd. They were up here because they had agreed to build a road up to this site. There was no road up here at the time. And they had to have a good quality road in order to haul all of the heavy equipment and telescope parts up to that plateau. They agreed to build the roadside, and it was an essential step in putting the observatory up here. They built the road, and it was called the Highway to the Stars. Well, it may be the highway to the stars, but it was a pretty rough road, pretty rocky road. Here's a portion of it just below the observatory before they got the road surfaced. It was a tough construction effort, and the road itself reasonably dangerous. Not entirely sure how this car got turned this way, but it happened, and sorry to say, it happens still. Well, with the road in place, they began setting up the location for the observatory. And here you'll see off to the left, over on this side, there's a water tower and there's a big water storage tank, both of which are still in place. See, they had to pour a lot of concrete for the walls and foundation of the 200-inch telescope. So one of the first things they did was drill some wells, put up a water tower, so they had water available for the work. They needed to get infrastructure in place on the mountain. And here you see workers in the process of grading roads. And in the background, you can see the water tower. And in front of the water tower, this building is what we now call the powerhouse. Well, there's a good reason it was called the powerhouse, because at the time it contained 3 Enterprise diesel engines that were used to generate electrical power for the observatory. This was a pretty remote place in the 1930s. There was no connection down to one or more of the power companies down below. And we continued to generate electricity using the diesels until the mid-1950s. So as the infrastructure got put in place, here is the site for the 200-inch telescope. The black circles are for footings for the walls of the dome. And in the center of that circle, they built this structure. It supports 530 tons of telescope up on the observing floor. The structure goes down 22 feet into the bedrock of the mountain. And as a result, we haven't had a major issue with earthquakes. So the walls went up around that structure, excuse me, it's August 1937. And we see it here where steel has gone up to the top of the walls. And on the top of the walls, they put a system of rails. You see, the dome has to be able to turn. The dome has two slits that open, make a 30-foot opening, and it has to turn to keep that opening above the telescope all night long, wherever the telescope is looking. And what they're doing here, they got this strange contraption sitting on the rails. And for 5 months, they used this to smooth and polish the rails. They had to do this. They had to do this because the dome will be rotating during exposures. We used to take some very long exposures here. And they had to prevent a situation in which rotation by the dome created vibrations, and those vibrations got transmitted to the telescope. It would ruin the images. So they spent a long time working on those rails. And here we see the dome going up. The two arches will be used to support a 60-ton crane. And the crane will be used to raise the mirror, raise other parts of the telescope up onto the observing floor. I should note that in some ways, this was a different time. That sign says all persons entering this building enter this building at their own risk. Well, there were few safety rules. And in this case, we see somebody, a welder, sitting at the top of the dome, partially completed dome, 135 feet above the ground level. And as near as we can tell, he's got no safety harnesses on. And that's the way they did business back then. Well, as the dome was going up, at the same time, they were building what would become our visitor center. And also, they were preparing for two other telescopes. On the left, you see the walls of the dome that will house the 18-inch Schmidt telescope, wide field Schmidt telescope. And on the right, you see the walls that will support the dome, excuse me, of the 40-inch Schmidt wide field telescope, excuse me. And all this was going on at one time on a budget of $6 million. Well, the 18-inch telescope seen here in the optical labs at Caltech, that was an important innovation. It was used initially starting in 1936 by Fritz Zwicky, who used the telescope and took advantage of its wide field characteristics to search for supernova. And he found quite a few of them. But you see, the importance of it is this set Palomar Observatory down a particular path one that is still very much committed to. Surveys have been a key part of what we do from 1936. Here, Zwicky is doing a survey looking for supernova. Now we're doing surveys using digital digital techniques to look for transient items. It's a system called the Zwicky Transient Facility, and we have discovered in the last 2.5 years several thousand supernova. We've discovered near-Earth asteroids, all kinds of things that appear suddenly and then disappear, and we capture them in digital media. Well, all of this, here's the crew who working on the dome, and they all got together to take a picture as the dome was nearing completion. And by 1938, the dome and the essential infrastructure of the observatory was complete. But as yet, there's no telescope. And that was being worked on at Westinghouse Corporation in South Philadelphia. And here we see all of the people who are working on the tube and the mounting of the telescope standing in a ring. That ring will sit at the top of the truss structure, holding the truss together and bringing the prime focus ring together with the truss. See a little bit more about that in a minute. Well, you see, Westinghouse was one of the few corporations in the country at the time possessing the kinds of presses and other machines capable of making the size and weight of parts needed for the telescope. Here we see another ring. This one is attached at the bottom of the truss tube, and we see it in a hydraulic press in the factory in South Philadelphia. Well, there were lots of parts. There were lots of parts to the equatorial mounting of the telescope. Here we see the south end of the yoke mounting, excuse me, 2 support tubes, east-west support tubes. And this will be joined together by the horseshoe bearing at the north end. And there's a whole history to this structure. This existed because the 100-inch telescope at Mount Wilson had a bar across the north end of the yoke mounting. And as a result, the 100-inch telescope could not depress in northerly direction beyond about 67 degrees. It could not reach the celestial North Pole. And that made one very important person very unhappy. And that was Edwin Hubble. Whole section of the northern sky he couldn't reach with the 100-inch telescope. And so Caltech engineers came up with this split ring structure to sit at the north side of the yoke. And now the telescope, 200-inch telescope, can depress all the way to the celestial pole by coming down into this structure. Well, here we get another look, gives you, again, gives you a sense of size. This is the ring at the top of the telescope that will hold the prime focus cage. And you can see a couple of people working, one person way up on top there. Again, gives a sense of size and scale of what they were doing. Well, they were working on the structure of the telescope, and in April 30th, 1937, they had essentially completed the truss structure, the tube of the telescope. And so they did a dedication for that part of the project. And they were in the factory at South Philadelphia. This is the only occasion we know of in which Albert Einstein was involved with the project. And you can see him there on the dais. Well, as construction went along, they finally got to the point parts were complete. In this case, that prime focus ring from the top of the telescope has been put on a rail car, taken out of the factory, and they took this and the other parts of the mounting out, took them down to the Susquehanna River, put them on a ship, take them down through the Panama Canal and around to the port of San Diego. Here is a part of the telescope. I think this is part of that horseshoe mount that is being unloaded at San Diego from the ship and placed on a trailer. And here we see that part headed uphill on the highway that the county of San Diego was still completing. In those days, it was a tough haul up the mountain. Notice here, we've got one tractor or two tractors that are tied together, and it looks like one of them has overheated. Apparently that was fairly common when they were bringing stuff up the mountain. As that may be, the first part of the mounting arrives on October 16th, 1938, and parts are staged on the west side of the dome, right in front of a big set of doors through which everything enters the observatory. And here you see again that prime focus ring, and behind that, that's the upper of the two rings that tie the truss structure together. Well, they staged them outside and then in order brought the pieces into the observatory. And here we see a part of the horseshoe mounting being hauled up through a hatch in the observing floor, where it's going to join some of the other parts you see over on the left-hand side. Well, from there, the assembly of the telescope moved pretty quickly. Here we see the west arm of the yoke supported on a scaffolding as the east arm behind it there is being raised into place. By February 1939, the yoke mounting was complete. And you can see in this photograph where the truss structure, the declination structure, is going to fit and be supported onto the yoke and will turn on bearings at those two, at the point we see here and the one across it on the east arm. Well, here the yoke is complete and the truss structure, the tube, is nearing completion and put in place. And you know, the tube can turn north and south, moves in declination, while the yoke structure we see turns east and west in right ascension, which is kind of how a equatorial mount works. And this was the last major telescope, major astronomical telescope to use an equatorial mounting. The reason is that all the structure we see here weighs 530 tons. And they couldn't make a larger telescope because of the weight it would impose upon the design. That's why this was the largest effective telescope in the world from 1949 until the Keck telescopes came online starting in 1993. They couldn't build a larger telescope until they could come up with computer controls that allowed the telescope to be mounted in azimuth and therefore at least relatively much lighter weight design. So here is the mounting nearing completion. And by late 1939, effectively, the structure is complete. Everything is done except there's no mirror. Well, George Ellery Hale had said the mirror is going to be the pacing item of the whole project. And here's the crew, now larger crew, who's going to do the work on the mirror. Over on the right-hand side, the gentleman in the suit is Marcus Brown, chief optician for Caltech. And they had to grind, see, it was a big job. They had to grind off 5.5 tons of glass to make that f3.3 paraboloidal curve. Big job. It was a big job because that paraboloid had to be very precise. They wanted an accuracy better than 1/10 wave. And what they actually achieved is a whole nother big story we can come back to later. But they thought the work would take 6 or 7 years to complete. Well, they thought it would take 6 or 7 years, but the telescope didn't go into service until November 1949. And we'll see some of the reasons that happened. Anyway, they get started on the grinding and polishing, and they built a turntable for the mirror, topped with a gantry structure that would hold and drive the grinding tool. And this is the grinding tool in position. The mirror blank would spin in one direction, and the grinding tool would make circular motions around the mirror and take off little bits of glass on each pass. Well, they were making good progress. By the summer of 1941, they had achieved parabolization, well, that's a tough word, parabolization to a first approximation. And they considered at that point the mirror to be 90% complete. But something got in the way. And in December 1941, the mirror project was put on hold, and they didn't get back to it until December 1945. And this is inside the optical lab. This is probably fairly late, probably taken fairly late in the process, because you see, for a lot of for a lot of, they only stood the mirror up on its side like that when they needed to do an optical test, when they needed to evaluate the accuracy of the surface. They did a knife edge test, and they had to set it up so they had enough room to get to the focal point. So here the project is moving along, and by October 1947, Marcus Brown and the administrator of Caltech decided that the mirror was done, that it had a good figure. And Marcus Brown, well, he considered himself something of an artist as well as a technician. He signed his name on the glass. And this is located right at the edge of the Cassia Green opening, where the mirror is shadowed by the prime focus cage. So they packaged the mirror up and started the journey to Palomar, November 18th, 1947. And this is the route they took from Pasadena to Palomar, down along the coastal highway. And here is the mirror passing the mission at San Juan Capistrano. They got to the city of Escondido that night, stayed overnight, and then next morning, they started up the mountain. Well, it was supposed to be a nice, warm, sunny, bright, late fall day in Southern California. It was anything but. Rainy, snowy up on the mountain, icy, and they were thinking they had a long haul to get this mirror up to the observatory. This is November 19th, and Byron Hill is on the top of the box. He was the construction supervisor and the first observatory superintendent. And what he's doing here, as the convoy is headed up the mountain, he has one tractor in front pulling and two tractors in back pushing. And his role, or one of his roles, standing on the box going up the mountain, was to yell to the drivers and let them know when to shift so that they would all shift at the same time. And here's a news clip of the mirror on its way to the observatory. Byron Hill does some pretty neat footwork there to maintain his balance. And here is the mirror coming into the observatory. You can just kind of see the dome back through the fog. So they got to the observatory about 11 o'clock. And then they brought the box into the ground floor, after which they opened the doors and brought it inside, at which point they unpacked the mirror and put it in a hoist to bring it up to the observing floor, at which point they put a coating of aluminum, reflective coating of aluminum on the upper surface, put it in the telescope for tests, and found out that it wasn't quite as done as they thought it was. Well, they had more work to do. The edges had not sagged quite the way they thought it was going to. And here you see one of the workers with a device He goes around and around the mirror, and he's very slowly taking that edge, taking the upper edge off of the mirror. So they had, as you say, they had to go figure. And while they were figuring, Caltech held a dedication for the telescope, June 3rd, 1948. And with a large crowd, Caltech president Lee DeBridge announces that this will be named the Hale telescope. Well, lots of things going on at the same time. While that's happening, the 48-inch wide field Samuel Ocean Schmidt telescope goes into service. Can I help? There we go.
I'm going to mute everyone except for you, Steve.
Okay.
Just clear the deck. Okay. Okay, now you need to unmute yourself. In the lower left corner, you should find an icon if you wave your mouse around.
Got it. Got
Okay, good. We hear you. Thank you. Sorry about that.
Oh, no. And here we see Edwin Hubble at one of the guide scopes on the 48-inch Schmidt telescope. He's got the control panel. He's got a tweedy jacket on, and he's got a pipe firmly clenched in his teeth. Of course, Edwin Hubble thought they had built the observatory for him. But as that may be, with the, try that here. With all of that in progress, they're finishing the figure of the mirror here. A worker is at the mirror, and he's got a little bit of rouge, and he's taking individual layers of glass off of the surface to try to get to a perfect paraboloidal curve. Well, the opticians would have kept up at this forever. They wanted a perfect surface. And as it turns out, the astronomers wanted their telescope. And here we see Edwin Hubble looking a little bit sour, sitting at the prime focus cage. As it turns out, the figure of the mirror is better than will be supported by the average seeing conditions here. And that's the argument that the astronomers made. They wanted the telescope, and Edwin Hubble was given the honor of taking the first light photograph on January 26th, 1949. This is an image of NGC 2216, which, as it turns out, has the nickname of Hubble's variable nebula. He thought that was appropriate. Now, Hubble didn't discover the nebula, but he discovered that its luminosity varies. So he chose as the first light image of something that bore his own name. Well, the optics are coming together. They still got work to do on the control systems. And here you see they're working at the old control desks that is out on the observing floor. That took a couple more months. Then finally, November 1949, Here's the first page of the 200-inch telescope's observing log. And with that, the telescope was commissioned and went into service. Science programs began at Palomar Observatory November 13th, 1949, and have continued to the present, with us observing on average 300 nights a year for the last 71 years. And with that, that's my story of building Palomar Observatory, and I'm sticking to it. Lord Ellery Hale had a motto. He said, "Make no small plans, dream no small dreams." And when he thought of Palomar Observatory, I guess he was thinking pretty big. So thank you very much. I love this subject. I have a great time with it. Thank you for listening to me.
Thank you very much, Stephen. That was really great. I think we all enjoyed it. Why don't we take some questions now? If you'd like to ask Stephen a question, please unmute yourself first. I believe everyone is muted except for a handful of us.
Hey, Stephen.
Yes.
The failed first mirror blank you said is in the museum. Is that still there today?
Yes, it is. It's the Corning Museum of Glass in Corning, New York. And they
cool to see.
They have no problem charging people an admission. I think it's now up to $8 to see, among other things, a failed piece of glass.
Yeah.
we always think that's pretty good. That's pretty good. Other things.
Steve, Sean, who doesn't have a mic, is asking, why is the observatory called Palomar?
It's on. Oh.
Well, the observatory is called Palomar because it was built, on Palomar Mountain.
I'm unmuted.
Now, where the name Palomar Mountain came from is a matter of some dispute. Don't really know. Some people have said that Palomar in Spanish refers to a dove.
Giving her all she's got.
We don't know for sure.
It's it wide open.
The Illumina was put on when it was in the building already.
Oh, yes.
Why was it the aluminum put on then, and how did they do it?
Well,
Just illuminizing chamber there.
we couldn't do it prior to the mirror's arrival because we used a vacuum deposition process, and it
Sorry,
required.
it seems like there's a lot of noise in the background. Is there somebody that's unmuted that's got a TV or something going there?
Yeah, unless you've got
Sorry
a
to
question,
interrupt you.
if you're not involved in the discussion, please mute yourself. Okay, continue. Go ahead.
Okay, that vacuum deposition process requires a huge vacuum chamber. Vacuum chamber that in diameter is bigger than the mirror itself, because the mirror has to go in there. And what we do, I've been involved with a couple of reilluminizations now. We take the mirror out of the telescope and bring it over to the work area where the vacuum chamber is located. We take the mirror over there, we clean off the old coating of aluminum, and then the bell jar that goes on top of the structure, the inside is lined with 360 tungsten coils that are impregnated with aluminum. And the top is put over the chamber. We draw a vacuum and 10 to the minus 7 or 8 torrs, something like that. And then they fire off those tungsten coils, makes a plasma that coats the inside of the chamber and leaves a thin coating of aluminum on the surface. No more than, you know, a couple of angstroms thick. And that's basically how we do it. Caltech invented that process, and it was first used in 1934, I think, on the Crosley refractor at Lick Observatory. Maybe more than anybody wants to know.
Sounds real easy.
Oh, it's a 8 to 10 days, all hands on deck process. And, you know, not only is it a whole lot of work getting the thing clean and doing all these pieces, but it's a bit stressful because to some degree it's well, maybe as much as an art as a science. There have been times when it hasn't worked and it has to be redone, and that gets people truly upset.
I'm also amazed at the precise measurement that has to be made to get the right curvature on this huge piece of glass. How can, and it looked like somebody was working by hand on one spot there or something. How can they be so precise? How do they measure that?
Well, particularly in that process in which they were doing the final figuring there on the observing floor. What they did, they used a different optical test, a thing called they put what's called a Hartmann screen up on top of the telescope. I guess the procedure is now, I think it's a Hart-Shankman test, which is done on a computer, but then it was all done in analog form. And they had this screen up on top of the telescope with 400 little round holes in the screen, very, very precisely placed. And what they'd do is they'd take pictures of a bright star through this screen on an unilluminized mirror. They'd take pictures before focus and pictures after focus. Then they would compare the position of the dots on the exposure, their positions with the positions of the holes, the round openings on the screen. And where things didn't line up precisely, they knew they had more work to do on the surface. So they would do a test, evaluate it, make adjustments to the surface of the mirror, and then go back and test again. And they did this over and over and over again until they got what they thought was a pretty good surface. It was a long process because, you know, we saw that guy with the rouge out over the mirror there.
Yeah.
When he does that, they then had to wait at least 19 hours for the surface of the glass to cool after the friction. So for this whole period of time, they were doing really very little work on the actual work on the mirror. They were sitting around waiting for it to cool after they'd made some adjustments.
Because of the change in temperature when he rubbed it.
Yep.
Oh, wow.
That friction created enough heat to alter the figure of the mirror.
Absolutely astounding.
And you know, another related point that's kind of interesting, I think, toward the very end, they had an astigmatism that they just couldn't get rid of. And one of the people up here, whose name I'm missing at the moment, had just an inspired moment. And he went down the mountain to a sporting goods store, place called Lake Henshaw, and he bought 4 fish weighing scales. You know, these little things where it has a hook in the bottom and a scale, and you can get the weight of a fish on. And he hung these at quadrants on the back of the mirror and carefully adjusted the tension on each scale. And after some back and forth doing that, astigmatism disappeared. And those fish scales are still in place.
Oh,
How did it? I'm sorry, what did the fish scales do?
They pulled very tiny amounts. They put very tiny amounts of pressure on the back of the mirror and brought it into shape. I mean, literally ounces, equivalent ounces of pressure.
So like
on the back of
tilted the mirror sort of.
Excuse me?
It tilted the mirror slightly?
Well, it tilted, it adjusted the surface very, very slightly.
Well, it
Enough-
doesn't change the surface of the mirror. The whole mirror itself is going to be tilting by the weight pulling on it.
no.
Well, imagine the telescope pointed straight up and the mirror lying flat. Yes, they would pull on the mirror, and they pulled on it enough to bring it into exactly the right shape. Now, there's another issue that you raise there. As the telescope moves back and forth across the sky, you know, it's 14, you know, once they got the paraboloid made, it's 14.5 tons of glass. 24 inches thick on the outside, 19 inches thick on the inside of the Cassia grain opening. And this thing's going back and forth across the sky, and the glass is not